able to watch the videos that are recorded in case you need to refer to them. And also the assignment one is released based on the discussions in the last class. Hope you're able to access them as well. So continuing our discussion, so we talked about directional vectors. So from that we build on to the notion of gradients and basically supporting hyperplanes on gradients, which help you understand convex functions from the notion of a set. So there's another perspective on convex functions from sets, which is quasi-convex functions. We talk about quasi-convex epigraphs, we'll build on that. And all of this now starts making sense when you look at first order conditions of convexity, subgradient and its calculus. Proofs we are not doing in the class much, but the intuitions is what we'll focus on. And then we'll move on to other concepts like Lipschitz continuity and so on. So this is the outline, which I just have in the title. So let's delve on the homework problem we had with respect to what we call as quasi-convexity. So we talked about the direction vector, right? It was a recap, and the directional derivative on the gradient. Then we talked about the directional derivative basically along a vector v is the dot product of the gradient at that point with vector v itself. So then we went to the notion of a sublevel set. So how is all this coming together? Well, basically, if I have, and we'll visualize through a convex function, then the sublevel set is basically at a alpha value is the set of all x such that fx is less than or equal to alpha. Okay, so if you have the function in let's say 3-dimensional space, okay, x1, x2, x3, this is a convex function. Now, if you were to consider how it might appear on the x2, x3 plane, if you do that, in fact, x1, x2 plane, this is fx1, x2. This is a function axis, x1 and x2 axis. So if you start looking at how the space of x1, x2 such that fx1, x2 in this simple case is less than or equal to say alpha. This would what it would look like. This L alpha for the function, L alpha for the function n. This is a sublevel set. Okay. Now, if you change the value of alpha, the sublevel set will change. Okay. So this is basically at some value. Let me. This is alpha, right? If I change this alpha to alpha prime, this is alpha prime, and you have a corresponding sublevel set L alpha prime f. Is that clear? So this sublevel sets, shown on the board as well and the slide as well. The sublevel sets are basically in the space of x1, x2. The function is in the space of x1, x2, comma z. You can call it z or f of x1, x2. I mean, f of x1, x2 is a value. Ideally, I should call this axis the z axis. This is the z axis, the function axis. Okay. So now, what is this connection with directional derivatives, gradients, right? We're going to see that very soon. Let that evolve. And but the point with sublevel sets itself is that interiors of these level curves are expected to be convex. If the function were not convex, if the function were like this, right, then f of x1, x2 such that f of x1, x2 is less than or equal to alpha, would look convex. Right? Less than equal to will mean this side and this side. In fact, the sets may even be disconnected. You understand? If the function was like this, then your set might be here, union here, right? Disconnected sets. So it won't even look convex. It won't even look connected. Forget about convexity. Okay, so this. So the point is, if a function f is convex, its alpha sublevel set is a convex set, which we a very simple proof, right? I gave the proof. It is basically taking linear combinations, convex combinations of the function value, of the points, evaluate the function, which is less than equal to the convex combination of the function values, which is less than equal to alpha. So, right, if f of x1, x2 and f of x1 and f of x2 are both less than equal to alpha, then the convex combination is also less than equal to alpha. And as a result, the function and the convex combination will also be less than equal to 1. Very straightforward. But what we saw, a problem was, if the sublevel sets are all convex, right? Then what happens? Is the function necessarily convex? And what was your intuition? No, right? So that's where we left off as a homework problem. And I gave this example. Okay, so same thing I'm showing here in this figure, what I showed on the board, alpha 1, etc. Yeah, so shrinking alpha will correspond to downward movement along the function axis. So as you shrink alpha, you have to move down. That's why convexity of the function gels very well with the convexity of the sets, sublevel sets. So what if now there's something else called the epigraph. Okay, I'm just as I mentioned last class, I'll put that thought in your mind. We'll revisit it. So the notion of an epigraph is in x1, x2, z plane, in three-dimensional space in this case. So this is the epigraph. If I have to consider, it is green. Sorry, I'm not finding a better color. Maybe orange and green together. Okay, this entire space above. This is the epigraph. And it's called EPF. Its name is basically set of all points x1, x2, in this case, x1, x2, comma z. Okay, so three dimension, such that f of x1, comma x2 is less than equal to z. So all the points basically lying above the graph. Epigraph means every point lying above the curve. So it's little obvious that if the function is convex, the epigraph is also convex, right? We'll not prove it right now. We'll say later on. But do you also get an intuition that if the epigraph is convex, the function also may be convex? If the epigraph in this additional dimensional space is convex, it appears that the function should also be convex, right? But that doesn't hold with the sublevel set. Okay, so epigraph, if I deliberately bring out this contrast, f is convex if and only if epigraph of the function f is convex. Okay, but however, um, L alpha f is convex for all real alpha if f is convex. Though the converse does not hold. By converse, we mean even if L alpha F is convex for every value of alpha, F may not be convex. So what if the sublevel sets are convex? Do they imply this function is also convex? Did you try proving this for any function, Gaussian, any homework attempts? Anyone? It's a simple function. This simple function is obvious. Log of absolute value of x is less than or equal to alpha. Alpha 1. Do you see that each of its sublevel sets is convex? Right, I have written on the board. Log of absolute value of alpha x is less than or equal to 1 if and only if absolute value of x is less than or equal to e raised to alpha 1. And that you can easily mark, right? It's basically e raised to minus alpha 1 to e raised to alpha 1. That's a fixed interval. And it's basically closed convex set. It's an interval, closed interval. That's it. So it's a convex set. So you can see that this, all the sublevel sets are convex. Is the function log of absolute x itself convex? Any thoughts? Why? How do you know that log of absolute value of x is not convex? Okay, so with scalars we know you can always scalar valid functions or functions on scalars. One dimensional case. Log of absolute value of x is log of x if x is greater than equal to greater than 0. Is log of absolute value of x defined at 0? Undefined at 0. Okay, in any case, the derivative here is, double derivative here is what? X greater than 0 will mean? Sorry? Minus 1 upon, which is here it will be what? Again negative. So what do you conclude? Can it be convex? Not convex. Get plot it as well. Okay, let's take a more appealing example. This seems very contrived, but the example we took was of Gaussian. Okay, so this converse doesn't hold is very easy to show. Right? I'm not proving it in the board, but converse does not hold. To illustrate, I have considered another function as well. F of x is x1 by 1 plus 2 x1 square. So I have showed that, well, if it's not, the sublevel set is convex even for one value, doesn't mean that function is convex. So sublevel set is convex for 0, right? But it is not convex. Function is not convex. What I am showing on the board and the previous slide was, even if the sublevel set is convex for all values of alpha, it is not convex. The function is not convex. More examples. Right? So this is. So before I get to more examples, the definition of a quasi-convex function is one, all of whose sublevel sets are convex. Okay. So quasi-convex means exactly this. The converse, right? So F is quasi-convex if L alpha F is convex for all real alpha. So what we are basically saying is, now we are trying to prove the others, which is that the set of all quasi-convex functions, is it a subset or a superset of all convex functions? Sorry? Subset? If f is a quasi-convex function, does it have to be a convex function? But if f is a convex function, it is a quasi-convex function. So what is a subset of what? Right. So convex implies quasi-convex. Right. So in one sense, we are saying that this is your space of quasi-convex. Sorry, I should show a bigger one. So the bigger one is quasi-convex, and the smaller spaces of convex functions. So what I do in the board here is to show an example of a quasi-convex function which is not convex. Okay. So we are saying that one example of such a function is a negative of the Gaussian function. That is one such point. Negative of the Gaussian function is one point in the space. Okay. And so I've taken a simpler example on the board. So f of x is minus of exp x minus mu square. This is basically what is the standard deviation or variance here? Sigma square is 1 by 2 pi. So basically I try to get rid. I've also discounted a multiplicative factor, doesn't matter. There's a scalar. But yeah. So sigma square is sigma square in this case 1 upon 2, right? Sigma square is 1 upon 2. Okay. So what have I done here for this? F dash x is, you just take 2 into x minus mu, exp of minus x minus mu square. F double dash x you can again evaluate. Very similar to what I did for the case of log of absolute value of x, right? And the second derivative is negative if x is greater than mu plus square root 1 by 2, or if x is less than minus mu minus square root 1 by 2. Okay. So the derivative is not non-decreasing everywhere. Or in other words, the second derivative is not non-negative everywhere. You understand, right? The derivative, if it has to be non-decreasing, then how should the second derivative be? Non-decreasing means not strictly increasing. Should have been non-negative. This is not non-negative everywhere. Okay, don't get non-negative. You can think of it as just not positive. Okay, the reason we are using non-negative is it may not be strictly positive, but positive generally means positive, strictly positive. So you're using non-negative to mean it is not strictly positive. Okay, replace all non-decreasing with increasing if you want. Replace all non-negative with positive if you want in your mind. But this is the correct technical statement. So function is basically not convex everywhere, even though. So that's the second example. Same procedure we have used. Similarly, negative of the Gaussian. So it is quasi-convex but not convex. Okay. You can show that it's quasi-convex very easily. But what I'm going to do is I'm going to do some more illustration. Okay, so this, so we are trying to show that the negative of the normal distribution is quasi-convex. Okay? But we'll try and do it graphically. And what we'll do is basically this is the Gaussian, take the negative and try and visualize the sublevel sets. We are ignoring some multiplicative factors to show that, example of a quasi-convex set which is not convex. Okay, let's look at this. So here, yeah, these are actually super level sets. So if you imagine taking negative of this, then you will find these to be the sublevel sets. This is a sublevel set for the negative of the Gaussian, or what is called super level sets for the Gaussian itself. Super level set is basically the same. The inequality greater than equal to will be, less than equal to will become greater than equal to. So doing greater than equal to for the Gaussian is the same as putting less than equal to for negative of the Gaussian. So anyways, this is what you typically see in all your many slides. So you'll have these, you can see all these discs, concentric, not concentric, but these discs are all convex. All sublevel sets are convex. Okay, so this helps complete the picture on quasi convexity. So question will be, all this is fine. Now, why is quasi convexity of interest? Well, it turns out that quasi convexity itself is a very interesting area because it just helps you look at a larger class of functions which have many nice properties. Okay, so it's inspired by convexity. How is it inspired by convexity? I'll be showing one more illustration, but let's take the same example right here. If all these disks, concentric disks, are concentric, I'm using very loosely here. If all of them are convex, then what you could possibly do is think of some rate of change. See, as you are going out, right, the alpha value is increasing. The threshold is becoming more benign. So you basically can go from outer regions to inner regions. You can define trajectories. If you want to minimize quasi-convex functions, you could think of trajectories. And what should these trajectories be? These trajectories should be orthogonal to some tangent, right? And will a tangent exist or supporting hyperplane exist? We know supporting hyperplane exists for convex sets. So you see many nice properties of convex sets I can exploit if I discuss quasi-convexity. And these supporting hyperplanes are what will also be connected to what we call quasi-gradients, okay? Or subgradients. Actually, there's something else called quasi-gradient also. So this brings me to the next question. So same thing I'm trying to show here. All right, you have this negative Gaussian, and I'm saying that, well, what if I look at these concentric circles and have some kind of a trajectory for moving from one circle to the other? Something like this. Okay, and that can be connected to the notion of a supporting hyperplane. So what could be good algorithmic principles for optimizing? I'm just going to give you some interesting reading for quasi-convex functions. So beyond convexity, stochastic quasi-convex optimization. This is a paper in 2015, NeurIPS. Spider near optimal non-convex optimization via stochastic path integrated differential estimator. 2018 NeurIPS. You can see Uh, there's been more recent work on Quasi Convexity, right? And then stochastic variance reduction. How can the variance be reduced in the way the steps are taken, and so on, and adaptive methods for non-convex optimization. So yeah, I'm not going to delve more into it. So this is just a proof that the function is quasi-convex. Okay, so sorry. Yeah, to sum it all, uh, the negative of the multivariate normal density is also convex by inspecting its sublevel sets, which are nothing but ellipsoids. That's what I tried to show. They're all ellipsoids, the sublevel sets of the negative of the normal distribution. That's how you can show it's quasi-convex. Okay. Okay. Now this, I'm coming back to my interest in the next few topics, moving on from quasi convexity. So how can I look at um, the application of sublevel sets, supporting hyperplanes, all of that? In fact, even the notion of epigraphs to actual optimization. Sorry? This is e raised to minus, no, this is e raised to minus alpha 1. No. Yeah, that's, I'm saying this one is a positive interval. E raised to minus alpha 1. This doesn't contain 0. They're okay? Both are positive. Okay. So yeah, we have done with machine learning losses. So what I'm trying to say is, well, can we look at these just first order convexity conditions in terms of epigraphs and sublevel sets and so on, and apply not just gradient, but develop something called subgradient calculus, which becomes very important with deep networks, especially. Most of modern day ML is based on subgradient calculus, right? And then there also you find that subgradient calculus is also often used to learn the not just learn parameters of a network, learn sometimes the architecture of a network itself. Uh, so before I move on to subgradients, one last topic, which is epigraphs, which I have shown here on the board. But what is epigraph? It's formally defined as x comma alpha. I use z there in the board, but this is x comma alpha also, such that f of x is less than or equal to alpha. Basically, the set of points lying above the graph of f. And so epigraph, the other understanding of epigraph, now I'll come back to the supporting hyperplanes again, right? So imagine you take this supporting hyperplane to the epigraph here on the board, right? Sorry, to the sublevel set. This is a supporting hyperplane for convex sets. What does it mean in terms of the epigraph itself? Is there a way I can extrapolate this from x1, x2 dimension to the x1, x2, z dimension? What would that correspond to? Can I construct the supporting hyperplane for the epigraph from the supporting hyperplane for the sublevel set? Yeah, you see sublevel set, this has a supporting hyperplane. How do you construct the supporting hyperplane for the epigraph at a point here? The same point here. Just stack them up. Stack of all the sets, right? So it looks something like this, right? It'll be a plane. Sorry, this requires 3 dimension, but it'll come out like this. You see? It's not different. So So basically, this is a half space. You see that this supporting hyperplane defines a half space, and the epigraph is on one side of the half space. Both of these and blue are supporting hyperplanes. So all I've said in the board is, yeah, half spaces are also kind of epigraph. So this is an example of the epigraph for an affine vector. So here you have an affine vector, affine function, and now you consider its epigraph here through the half space above the. Okay. So I have now shown this whole thing in terms of epigraph alone. This is the set of all points lying above the graph. Sorry. Huh. No, but if you're looking at acha, minus e power alpha. Oh, wait a second. Hmm. Yeah, sorry, you're right. So there should be a negative. And here we seem to assume that, okay, this was my cooked up example. It seems to have some small hitch. Sorry? Yeah. But positive part in the sense you're saying, yeah, then let's go back to the board and we can say it's defined to be 0. And then define it to be 0. Yeah. Okay. Yeah, I made a mistake. Thanks. This is thanks for the correction. Okay. Okay. So this is summarizing what I've discussed so far. With sublevel sets, sublevel sets may be convex, the function may not be convex, and that's the case for quasi convexity. Every convex function is a quasi convex function. On the other hand, with epigraphs, epigraph is convex if and only the function is convex, and it's very simple to prove that, and that is depicted through this entire shaded green region. So this can be proved easily. Okay, so the one-to-one correspondence between functions and their epigraph convexity is very simple to prove. If D is a non-empty convex set, then what will you say? F is convex if and only if epigraph is convex. How would you prove that? F is convex if epigraph is convex is very simple. Proof is similar to that for sublevel sets. Exactly the same. So x1, x2, xn alpha is a point in epigraph. x1 prime, x2 prime, xn prime, alpha prime is a point in epigraph. Then theta times, if you consider the convex combination of these two, that will be a point in epigraph because the convex combination function and the convex combination of x1 to xn. Yes. What will happen to that? Sorry, of x1 to x1 and x1 prime. Function and the convex combination of x1, x and xn prime will be less than equal to the function, the convex combination of the function of the 2 points. by a convexity of f. And in the convex combination of the function, the 2 points will be less than equal to the convex combination of alpha and alpha prime. So it's the same thing. The three inequalities of which you just need to use transitivity. This is very simple. Okay, that's what I proved. I mean, this is more detailed. The previous slide, I just gave you the intuition. So you have this inequality. This is by convexity, and this is the second one is by epigraph nature. And therefore, you'll have the left-hand side is less than equal to the right-hand side. So the necessity part and the sufficiency part. So you have to basically show that if 2 points are in the epigraph and a epigraph is convex, then the function must be convex. Again, that's not difficult at all. I mean, it's basically you look at it and think what big deal. I mean, just the same thing being spoken in a different language, right? Okay. Now we come to the most important part. All of this is leading to this first order definitions of convexity. So I'll erase this part of the board. Sorry? Okay. Okay, we can, I mean, I think it's not such an important problem. The negative of the quotient should be good enough. I just came up with another example. Try to come up with another example. Okay, let's do this, which is more serious business. See, what we are trying to show here is this hyperplane, supporting hyperplane, whether it's for the epigraph or for the quasi-convex sets, the level sub-level sets, they have their origins in gradients. That's what we're trying to show. Okay, so this is the function space, and yeah, we said this is the epigraph. Epigraph is convex, and therefore it's important that there is a supporting hyperplane. Now, what is the equation of that supporting hyperplane for a convex? If the function f is convex, what is equation? Well, we have an equation for that supporting hyperplane. If this is the point x, okay, then supporting hyperplane at x comma fx, to be more precise, right? It's in x plus 1 dimension, right? To the epigraph of f is exactly what is specified on the right hand side of this equation. F of x plus the dot product of the gradient at x. Well, actually, yeah. I think that's okay. That's fine. Yes. And what we are saying is for every point y, every other point y, which is in the domain, x comma fy will lie on one side of the hyperplane. Okay. That is, sorry, y comma fy. Y on upper half space. Will lie on the upper half space of this gradient based supporting hyperplane. At x comma fy. Okay, sometimes it helps to write in plain English what these inequalities are depicting. Okay, we had this hyperplane. And we are saying then at point X, this is exactly the supporting hyperplane, so that the epigraph lies on the function lies above it. Epigraph of the function lies above it. Okay, so this is for convexity. For strict convexity, what happens? For strict convexity, instead of saying lie in, you will say what? What's the qualifier? Will strictly lie in, not even touch, basically, right? So here you see that some touching is going on here. It says, I mean, it could possibly it may touch in multiple places. For example, if it's an affine function, it might even coincide with the hyperplane. It could, right? But here it could basically meet at a infinite number of points. So strict convexity would basically imply, well, that x comma fi will lie strictly line. That is what that second inequality is. And the strong convexity, it says, well, not only will it lie above, but there must be some margin. Okay. So we'll write down the case of strong convexity. Okay, so now the margin is a function of the distance between y and x. So it depends on which point here and which point on the y you're talking about here. Which point here. So if you're somewhere here, then you're saying the gap should be at least y minus x norm square. That at least proportional to the distance between y and x squared, Euclidean distance squared. So C can be obviously 0 in the case of convexity. If C is not 0, then strong convexity would also imply what? Strict convexity. A strong convexity, if for non-zero C is a strict convexity also. Okay. So yeah, whatever I was trying to show on the board here, I've tried to show it again. Yeah, I think I should have used, yeah, this function. This is the gradient. So f of y is greater than or equal to f of x. This is part above, right? And yeah, I've shown the connection with epigraph. You can also see its connection with the sublevel set. Sublevel set, basically the supporting hyperplane is just going to be projection from the epigraph. That's it. So I have a question here on the side. Does this non-convex set? So what have I done? I mean, yeah, there's a gap here, right? Small gap here. Might remind you of the log example. Small hole here. Does this convex set have a supporting hyperplane at x? So this is non-convex set, sorry. Non-convex set. Does it have a supporting hyperplane at this point? So you can consider this to be a gap, or let's say this is a point and the interior is empty. Does it have a supporting hyperplane? No, right? So it's very somewhat intuitive that the notion of supporting hyperplane is very closely tied with convexity and gradients. So how do you prove it? Right? We want to prove that a function is convex if and only if this is a supporting hyperplane. A function is strictly convex if and only if it's a strictly supporting hyperplane. A function is strongly convex if and only if the supporting hyperplane is supporting with a gap of C norm of y minus x squared. Okay, I won't do the proof on the board, but let's just understand the intuition. Sufficiency. What is sufficiency? Sufficiency means that, well, uh, and we want to prove it for all the three cases. So suppose these three hold, one or two or three, right? Which is the hyperplane inequality holds. If the hyperplane inequality holds, you'll find it's not that difficult, right? Let's say the C is 0 to begin with. If I do this for point y1, do this for point y2, take a convex linear combination of y1 and y2, functions at y1 and y2, you'll see that actually these inequalities work out very naturally. You'll end up getting the convex inequality. And for all the three, it's not difficult. So sufficiency is easy. Okay. So I'm just going step by step. F of x1 greater than or equal to f of x plus theta transpose fx x1 minus x at point x1. Likewise, f of x2 is greater than or equal to f of x plus theta transpose fx x2 minus x. Right? And then what I do? Adding 1 minus theta times the second inequality. So 1 minus theta times this x21 to theta times the first one. What do you get? Very simple. Theta f of x1 plus 1 minus theta f of x2. Because the right hand side, the x is not changing, right? It's at the same point x. So you'll find that you will have f of theta f of x plus 1 minus theta f of x, which will just become f of x. And if you take theta of this plus 1 minus theta times the other, what will happen is yes. X minus x. So this x will disappear. When you take, right, theta of this plus 1 minus theta of this, right? Then you'll find that this x disappears. X will get cancelled out. Okay, so this inequality is very easy. And you add strict inequality, you will get strict inequality. The strict inequality will be maintained. The only thing we need to notice is the strict inequality maintained? Right? The strict inequality can be violated. For example, if you're taking limits. In this case, there's no limits, so it's going to be retained. In the case of strict convexity also, therefore this will hold, right? Strict inequality holds. In the case of strong convexity, some algebraic manipulation is required, which is a little boring, but you can convince yourself, you'll get the same old inequality. Okay. So I'm not going to delve into it. The necessity part, let's do now. What is necessity? Necessity is saying that if the function is convex and if it's differentiable, right, then you should have the supporting hyperplanes must exist. Supporting slash strictly supporting slash supporting with a margin and so on. Okay. Necessity. So necessity, if f is convex, we must have this inequality. Now, how do I obtain this? So this is where you should pay attention. How do I obtain the dot product of gradient at x1 with x2 minus x1? Is there a way I can write it in terms of this? Yes, you should try doing this. This is an important step, and we'll only spend time on the important steps here, the trickier steps here. As a hint, this may have something to do with the directional derivative. That's why we talked about directional derivative. So do you think this is something to do with directional derivative? The dot product of the gradient with x2 minus x1, right? It's a directional derivative at at x1 in the direction of x2 minus x1. Okay, so it's clear? The scaled version of directional derivative is a scaled version. It's obviously not directional derivative itself. See, directional derivative would have been limit as theta goes to 0 of f of x plus theta y minus x minus f of x divided by theta. But now it's not normalized, it's unnormalized. So we are saying at this point x or x1 rather, what is the rate of change of the function at x1 along x2 minus x1. Okay, so what is this? Can you write down the exact expression, please? I've given all the hints. Can I write it in terms of the convex combination? So I want something like x1 here, f of x1 plus theta times something. Now please help me complete this. F of x1 plus theta times x2 minus x1. What is f of x1 plus theta times x2 minus x1? You see the same as f of theta x2 plus 1 minus theta x1. They're the same, right? So I've written it differently. This is the only trick. What else? Minus f of x1. The whole thing divided by theta. Just that x2 and x1 is not a unit vector, but that's okay. So it will be a scaled version of the directional derivative. But this is the definition. Right? Okay, so now how do you get to proving necessity? Actually, sorry, I have to do one more thing, right? I have to take limit. Limit as theta tends to 0. Okay, so the limit as theta tends to 0 of this expression will be what? Do I want to evaluate it or do you want to show some inequality? What do I know about the numerator here? Necessity, right? What can I assume about the function? It is convex. The original definition, first principle definition should hold, right? So what can I say about this? Because you know this expression is nothing but theta 2 plus 1 minus theta x1 minus f of x1 divided by theta. So what do I know about the numerator at all points? The numerator is linear combination theta into f of x2. That's it, no? Um, yeah. So this is less than equal to how much? Theta into f of x2. Huh? 1 plus theta into f of. See, all I've taken here. So look at this now. All I've done here is taken out this f of x. Sorry. Um, yeah. So I've taken this, correct. So I have basically taken this f of x1 to the other side, this one component to the other side, and divided the whole thing by theta, right? Hmm. Hmm. F of less than minus theta of f x2, x1, right? This whole thing is less than equal to theta f of x2 minus theta f of x1. Is this clear? This numerator. Okay, I can write this explicitly. So I'm saying this entire expression, the limit is less than equal to limit as theta tends to 0 of theta f of x2 minus theta of f of x2 minus f of x1. The whole thing divided by theta. Right, and this is what? Limit of this is f of x2 minus x1. That's it. Okay, so this inequality is this is a big key, right? We are basically saying that f of x2 is greater than equal to f of x1 plus this dot product. Okay, I can bring x1 to the other side. Sorry. So this is a necessity proof for for convexity. For strong convexity also will be similar. Will there be a catch with a strict convexity? So there's a catch with the strict convexity, right? If I had less than, strictly less than here. Strict convexity, strictly less than. After limits, would it remain? Sorry, would it remain less than or less than equal to? Right, so it actually start with a less. This is equal to. So the problem is there'll be a less than equal to. Limits may not preserve the inequality. That's the problem with limits, right? So that's what I've said here. In case of strict convexity, the strict inequality is not preserved when we take limits. Suppose equality does hold. So now I'm going to give a counter example. I'll say that, okay, let's say that there was an equality, which means let's say that even for a strictly convex function, for some x1 which is not equal to x2, f of x2 was equal to f of x1 plus this dot product, which means for strictly convex function, this point x2 is actually lying on the same hyperplane. Even though x2 is not x1, it's still lying on the same hyperplane. Right? Then we'll show that that's going to lead to some inconsistency. What is inconsistency? Okay, so that is a little more work. So I basically write for some theta between any theta between 0 and 1 open interval. So we are going to use the property of convexity, which is already proved, which is this inequality, gradient less than equal to this. But we also use this in conjunction, strict convexity in conjunction with the other two expressions. So this is what we proved, right? We use this when we use this condition, and this condition both, because we have non-strict equality here, and we assume that there's a contradiction at x2. So use these two conditions and basically show that this leads to a contradiction, where the left-hand side is strictly less than itself, which cannot be possible. Okay. So if you get intuition, it should not be difficult to work out. So that's the only point we need to take care of. Okay, so this the complete statement is as follows. Exactly what I showed on the board. I'm now depicting here. The linear approximation based on local derivative gives a lower estimate of the function, that is a convex function, always lies above the supporting hyperplane at that point. Lying above basically means the epigraph is supported. Okay, so I've kind of now shown this. It's the same whole figure. I've brought it back here in 3 dimensions. How does it look like? How the supporting hyperplane here is basically, when projected, going to look like for the epigraph. It's again a supporting hyperplane to the epigraph. Now it's possible that the epigraphs are all convex, but the function is not. So that becomes interesting. What if epigraph is not convex? Epigraphs are convex. I have a supporting hyperplane. Now we can extrapolate that to the function even if it's not convex. Okay, and that's one reason, gradient descent kind of algorithms work even for Gaussian functions. If you want to maximize a Gaussian, it can work. Okay, so second order condition. This is all about first order condition. But what comes to your mind as well, if I have a supporting hyperplane, then another way of saying is that the function is stubbed upwards. Right? That's a curvature, positive curvature. Okay. So so here we are saying that f of x, x1 plus, oh, sorry. From theta x1 plus 1 minus theta x2 less than equal to theta f of x1 plus 1 minus theta f of x2. This condition is equivalent. Now I can add a less than instead of less than equal to, but it's the same as saying the first order condition, right, which was that f of x2 lies above the hyperplane, the supporting hyperplane at x1. And we are saying this existence of supporting hyperplane is the same as claiming a positive curvature. And positive curvature is like saying that the Hessian of the function at x should be positive semi-definite. That's what I was showing in orange here. It's curved upwards. The Hessian is positive semi-definite. And the claim is basically that f is convex if and only if the Hessian is positive semi-definite. Okay, so it's not just if, it's an if and only if. It's equivalent. One small question. If I had to extend this to strict convexity and also strong convexity, how would I change this? I know what will change here. Strict convexity, this become less than. This will become strictly greater than. What will change here? Instead of positive semi-definite. You understand what's positive semi-definite? This is basically saying that all eigenvalues are greater than or equal to 0. So if you have strict, then what will happen to all the eigenvalues? They should be strictly positive. For strong convexity, what would you think will happen? Positive definite, that's it. So Here, see, for strong convexity, I had a half C y minus x square. Okay, so let's just try adding that here. And guess what would happen? Yes? Ah. And the same thing will become what? Will become Ci greater than or equal to Ci, which means the Hessian minus Ci should be positive semi-definite. So even if you subtract the C times identity, you will get positive semi-definiteness of the Hessian. Okay. Okay, so in fact, for log sum x, right? If you can go ahead and do the homework, log sum x, V transpose Hessian log sum x V. If you expand it, that's what Boyd does in his book. He shows that can be easily shown to be always greater than or equal to 0. See, positive definiteness, one way of writing it is all eigenvalues are greater than or equal to 0. The other way is of saying that V transpose Hessian V is greater than or equal to 0. All these are equivalent definitions of positive definiteness, right? V transpose Hessian V is greater than or equal to 0. So that's what Boyd does to show that log sum x is convex. Takes any V into the Hessian of that complex log sum x. V transpose Hessian of log sum x into V and shows that it's always greater than or equal to 0. It's not that difficult. But what I showed is also fine. The midpoint convexity and the composition, all that is also fine. So the intuition is that first order condition, the directional derivative is non-decreasing. Second order condition, the curvature is positive in every direction. So you can think of every direction. In every direction, you must have positive curvature. First order says the curvature, the directional derivative is not decreasing in every direction that you take. Right? So typically to show that Hessian is positive definite or positive semi-definite, this is the way. You should show that for all V transpose Hessian V is greater than or equal to 0. That's the best way to show. Okay. In fact, I've shown the log sum x here, how it looks like. Okay. So Hessian of exp is exp. Sum of exp is a summation of y of exp. So if you take the Hessian, I think Hessian is missing. Okay. If you take the Hessian here, Hessian of some exp, you'll basically get exps along the dimensions. Exp of xi, exp of xj, also along the diagonals. Right? And if you take a log of this, what will happen? I want the Hessian of the log of sum of exp. So sum of exp is easy to see the Hessian. What happens to log? You'll obviously have some 1 upon something, right? But you'll also have some chain rule. You can't have just 1 upon log, obviously. You'll have 1 upon that expression. 1 of exp, sum of exp, right? Exp in the numerator again for that particular component. Okay, so not very difficult. You can try doing that. I think now since assignment is out, you can try out using all these definitions wherever required. Okay, and on page 67 of the convex optimization notes, I have given a table of Hessians for some problems. So for example, log sum exp, I have shown this. It turns out to be, you'll have one, here you see 1 transpose z into diagonal z. Diagonal z was easy to understand. It's all the exps, right? In minus zz transpose, where zz transpose will now have all the cross terms. Zz transpose is a rank 1 matrix. You understand, right? So zz transpose will look like this: exp x1, exp x2, and so on. into a row vector exp x1, exp x2, and so on. So you'll have all those cross terms. The others are easy. Like for quadratic term, it's very easy. A x transpose ax plus b transpose x plus c. The b transpose will disappear. With double derivative, b transpose x will have nothing left, right? So all that will remain is a. X transpose ax, double derivative will just give you a. And I'll give you a rule of thumb, okay, from this. I don't want to write it, it's for your intuitive understanding. So if you have, like, every time you take a derivative, you knock off the term which has a transpose in the beginning, okay? So some enmity with transpose, okay? So some enmity that gradient has with transpose. So take the term, say somehow bring it into something transpose. The term, the vector that has a transpose at the beginning, that is the one that gets knocked off. So, I mean, you can think of it like that, right? So x transpose ax, if you take a gradient, you'll get ax. The second time you take a gradient, then it knocks off the one after that, is ax, x after a. But I mean, if you actually write down the double derivatives, that's how it will turn out to be. Sorry? Haha. Yeah, so this is half, so it's obviously, yeah. It's twice. So half of x transpose ax, get twice of, because it's a square, right? Square terms in one. Okay, any other question here? Negative geometric mean, again, you can try and write down the Hessian. Quadratic over linear is a little tricky. Like in the part in the denominator, 1 upon y, this part, we'll have a square first with a negative and then a cube. That's why you find all of these terms here. 2 upon y cube comes out. Okay. Okay, so I have shown this, for example, in some details for log sum x. This is quite important for us. So what I've done is I've shown, okay, what if the z is substituted? The z, as I said, is this exps of all the x1, x2, xn, right? So if I substitute, how do I end up getting the Hessian? So 1 upon, this is fine. But the other terms will turn out to be summation over zi. 1 transpose z is the summation over zi. That's in part in orange. The part in pink, diagonal of z is the sum of regular entries. Okay, and that basically is turning out to be P transpose zi. And so where, you know, so basically what we do is we treat xi to be vi square root zi. Actually, after all of this, you'll realize we are using the same Cauchy-Schwarz inequality. Finally, it's a Cauchy-Schwarz inequality that gives you greater than equal to 0. So number of inequalities that give you that is a few only, right? And you can go around the world, but ultimately when you say mangoes, then you have like small set of mangoes that get exported all around the world. So it's the same set of inequalities that get exported and repurposed in different forms. And that's the example of Cauchy-Schwarz here. Right? So this is kind of what reminiscent of what we did earlier. Okay, so I've given the methodology of proof here. Hope you can usually build on this. So this basically gives you the positive definiteness in terms of, or positive semi-definiteness in terms of this quadratic inequality. Okay. Now we go to the next important. We'll just get started. All this is fine when the function is differentiable. So you are all of this, curvature, Hessian, all that is okay when you have differentiable function. But double differentiable function. What if derivative itself doesn't exist? Right? Can I replace our friend here, the gradient friend here, with something that looks like a gradient. Because I know that if the function is convex, even if it's not differentiable, it has a convex epigraph. A convex set always has a supporting hyperplane. Why should I require the supporting hyperplane to be always in terms of the gradient? If the function is not differentiable, there should still exist a supporting hyperplane, right? How do I define, how do I even come up with that supporting hyperplane? So that's where subgradients come in. Okay. So to say that a function f is differentiable, I takes us to say that there's a single unique linear tangent that underestimates, right? This is what we mean by differentiable. See, but if the function is not convex, if it's turning upwards again, then you have a problem. It may look like a tangent here, but it's not going to be supporting. It's tangent, obviously, but it's not supporting, right? So convex, supporting is only when you are convex. But do you need a gradient if it's convex? Not necessary. So what we'll do, okay, the story is, we're going to replace this with something called H. So I'll not use, I'll call it H. Hx1. H is the hyperplane. It's for the hyperplane, but it is not gradient. Okay. Does there exist H? Well, there may not be any second order property now. So I can erase this. That may not be possible here. But with this H, I can remove the strong. So strong convexity is out of the window. Moment you say, right, all this. Well, strong convexity is not out of the window. I mean, you need to add some strongly convex function to a not differentiable convex function. But that's okay. Let's we can have strong convexity. So I take my words back. But currently we'll only look at this convexity itself. I want to know if this can hold even in the function. Does there exist at h at every x1 even if convex x convex f is not differentiable is not differentiable everywhere. That's the question we are trying to answer. Yeah, so we want behavior like a gradient. So your question is, why can't the H be like a some approximation to the grade? Exactly. Yeah, you're right. You're right. It's an approximation to gradient. In fact, it turns out to, so the definition is going to be such that it will turn out to be the gradient if the function is differentiable. If it's differentiable, you don't need approximation. It is the exact function, right? It's not the, well, it will be. Okay. I mean, that's what we would like, right? Define it, the subgradient to be such that it is the gradient if the function is differentiable. If the function is not, obviously, then there's no gradient. You will have a subgradient. Yeah, you're on the right path. So, okay, so this is the idea. Now I have shown a different function here. I mean, so far, all through, I was showing this picture. Like this was our mascot so far, right? But our mascot can be a little modified now. We are saying, well, what if the function is like this? You see this function? What does this remind you of? Hinge loss, right? So instead of a very rosy picture like this, I'm saying this is my function, hinge loss. But I'm saying, well, even if it's not differentiable everywhere, there's a kink out there, right? And I'm saying at the kink, at this kink, I can define a normal here. Sorry. Yeah. Hmm. Here. Here. This way. And I draw perpendiculars to these. So let me show it here. This is easier. So all I'm saying is there may not be one supporting hyperplane. There may be multiple supporting hyperplanes. This is a supporting hyperplane. This is a supporting hyperplane. This is a supporting hyperplane. Right? And I should have used a different color. And these are the subgradients. So the ones in pink, okay, let me use the pink. These are the subgradients. If you can draw this picture, it will be helpful. Right? This cone. This is a subgradient. And these, the ones in pink, these are the supporting hyperplanes. Okay, so I'll try and use the same color here. Okay, yeah. That's the same color, right? So this part in green is what correspond to subgradients. All the possible subgradients. And the part in pink are all the supporting hyperplanes. Is this fine? You're getting a picture of what we are trying to do? Okay, so I'm going to just define this so that the next few topics we really now go into subgradients and get into minimization. Okay, so subgradients. I just want to leave you this thought, right? So this is subgradient. Subgradient H is basically all the function is basically any vector which leads you to this inequality for all y's. So for a given x, if this inequality or given x1, if h of x1 is such that this inequality holds for all x2s, then we say that h of x1 is a supporting is a subgradient at x1. Okay. In this case, instead of x2, I have y and in place of x1, I have x. But it's the same. So thus intuitively, if a convex function is differentiable at point x, then what do you expect? If this is my definition of subgradient, then and if the function is differentiable, then sorry, yeah, then it will be a gradient. The subgradient will be a gradient. So I'm going to leave you some homework problems. Homework 1 is the subgradient So homework one is a subgradient guaranteed to exist at each point of the domain of a convex function, even if not differentiable. The optional homework two is, how do we show that for a differentiable convex function, the only subgradient will be its gradient. Okay, the two homeworks. Think about it. So the first one, is there an exception, or can we find a convex function for which there's no subgradient at some point? Or is there a convex function, right, where there's no subgradient at any point? The other way is to show, again, prove constructively that if the function is convex, there must be a subgradient at each point. That's maybe a more assertive way of saying it. And the homework two is saying, okay, if the function is convex, let's assume there's a subgradient at each point as per solution to homework one. Now, is it guaranteed that if the function were convex, then there's a unique, the gradient is unique? Will that subgradient turn out to be gradient at every point? How will you prove that? So, I mean, the proof sketch or the idea behind this proof is what is required, not the details. Okay, we'll continue on. Do attempt these homework problems. Give you the continuity across classes. Thank you.